right, this video is for the Algebra 2, Unit 6, Lesson 2, Part 1 notes. So we're going to be talking about modeling with exponential functions. We'll be doing, that's word problems with exponentials. So remember that in Lesson 1, we learned that exponential functions are of the form y equals a times b to the x. Now this a is called the starting value. And b, the number inside the parentheses, is called the growth rate. All right, so the number in front, the a, the first number you see is the starting value. The number in the parentheses is what we call the growth rate. So, for example, we have that the bacteria count in a swimming pool is 1,500 bacteria per cubic centimeter starting on Monday at 8 a.m. So you work at a pool, you check the bacteria, you start Monday morning with 1,500 bacteria. So let's fill in the table. It says that the bacteria count doubles every day. So times 0, that would be Monday at 8 a.m. That's when we said you had 1,500 bacteria. Now if you're doubling every day, that means that you're multiplying by 2. So 1,500 times 2 is going to be 3,000. And then we're going to keep doubling. So 3,000 times 2 is 6,000 bacteria. That would be on Wednesday. So here we're at Tuesday, Wednesday. On Thursday, the double of 6,000 is 12,000. By Friday, you have 24,000. And then on Saturday, the double of 24,000 is 48,000 bacteria. Now it says, what's the count on Wednesday at 8 a.m.? Well, remember, Monday was day 0, so Tuesday would be day 1. Wednesday's day 2. That means on Wednesdays, there was 6,000 bacteria in the swimming pool. Now it says, suppose you want to know the bacteria count on Thursday at 2 p.m. So it's 3.25 days since Monday at 8 a.m. So we're going to estimate our values. So we know if we get to Thursday, we're going to be somewhere here in between 12,000 and 24,000 because Thursday afternoon, Thursday morning is 12,000 and Friday morning is 24. So I don't know, I'm going to guess we're going to be close. I don't know, maybe 15,000 bacteria. It's somewhere in between 12,000 and 24. And we're just estimating, it doesn't have to be inaccurate. So if you think it's closer to 16,000 or 14,000, that's fine. So we want to answer that question more precisely, and I copied our table up here. To answer that question more precisely, we need to write an exponential function. So it says, if I began with a count of 1,500 bacteria, which is right here, how do I get the number after day 1? Well, we said that we doubled. Well, we multiplied that value by 2. Right? So we took our 1,500 and we multiplied it by 2. Now, how did we get the bacteria count after 2 days? Well, what we took for after 2 days, which is that 6,000, is we kept multiplying by 2. And here's what that looks like. We took that 1,500 times 2, and we multiplied it by 2, right? That's how we got the day 2 count. And then the next one, we would have taken that same value, that 1,500 times 2 times 2, and multiplied that by 2. We just kept multiplying our values by 2 over and over and over. So what's the pattern? Well, as the number of days increases, what stayed the same? Well, we still started with the 1,500, right? So I know this is kind of a funky way to write the expression, but each one of these all had a 1,500. But every time we multiplied by a new day, initially there was multiplying by 1, 2. And we multiplied by 2, 2 times. And multiplied by 2, 3 times. So the pattern here is that the number of 2's you multiply by increases. But the 1,500 stayed the same. So here's our equation. Here's what we have. We know an exponential, remember, is y equals a times b to the x. Well, our a is called the starting amount. The a is 1,500. 1500 here. That's the number of bacteria we start with. Now the number in the parentheses, the B, our growth rate, is what you're multiplying or changing by. And here we're multiplying by 2. So we have 1500 times 2 to the x, or here t power, but you could use an x. T is for time, that's always an exponent. So now it says use that equation to find the exact number of bacteria after 3.25 days. So I want to find the population of bacteria after 3.25 days. So I'll take 1500 times 2 to the 3.25. Now here you can use your calculator or you can use Desmos. Let's see, 1500 times 2. Since our bacteria is 14,270. There's a decimal, but we want to round to the nearest bacteria. So 14,270 bacteria. We guessed a little bit higher, but that's okay. It was just an estimate. Good. Go ahead and flip your paper over. Let's keep working on writing a model here. So this one is talking about the sound of music. It says, Maria makes a half gallon of orange juice on Saturday evening for Sunday's breakfast. In the middle of the night, Liesl got up and she was super thirsty. She drank half of the orange juice. She didn't want anyone to know she drank the orange juice, so she refilled the pitcher with water. Not long later, Friedrich woke up. He also drank half the pitcher of orange juice and had the same thought as Liesl. He refilled it with water so no one would know. Oddly enough, every Von Trapp child did the same. So let's fill in the table. At the start, at time 0, there were 64 ounces of orange juice. That's of what Maria made. Now, after Liesl came through, she drank half of the orange juice, which means that she drank half of it and there was only 32 ounces of orange juice left. She refilled the pitcher, but that pitcher still only has 32 ounces of orange juice. When Friedrich came, he drank half the pitcher, which took that 32 down by half to 16. This continues. Half of 16 when Louisa came would be 8 ounces. By the time Kurt shows up, there's 4 ounces of orange juice left in the pitcher. Brigitte drinks down to 2 ounces, Marta down to 1, and Gretel down to half of an ounce. I multiplied each of those numbers by 1/2. That's how I got the value. Now let's write a function. When we write these functions, remember, ask yourself, what's the initial value? How much orange juice did you start with? Well, 64 ounces. What's the pattern? Well, we're multiplying by 1/2. Or you could say we're multiplying by 0.5. So when I write my equation, it says write an equation that's f of x. You could do y equals. You take your starting amount, and you multiply it by the growth rate. Here it's 1/2 to the x. Now you could also write 64 times 0.5 to the x. That would be your equation. Now we're going to use that equation, and it says Sunday morning, Jörg wakes up and is so thirsty he wants to have some orange juice. Using the function we came up with, which was this, they want to know how much orange juice will be left after he has his drink. Well, he is going to be the 8th person here in our table. So we will take 64 times 1/2 to the 8th power. And go ahead and we can type that into our calculator or Desmos. So we'll start with 64 times 1/2 to the 8th power. And you get 0.25, 1/4 of an ounce. Not a lot of orange juice left. It might taste a little watery. Now suppose this pattern continues for 20 people. Will there still be orange juice in the pitcher? So we want to know 64 times 1/2 to the 20th power, 20th people. So let's change our equation here. Instead of 8, let's make this 20. Oh, it looks like it. It says 0.00006 ounces. So it has 0.00061 ounces. Technically, there is still orange juice. You won't be able to taste it probably. It'll just taste like water. That's a really, really, really tiny amount of orange juice. But technically there is still orange juice in the water. Now if this pattern continues infinitely, will there always be orange juice in the pitcher? Technically, yes. Again, it's going to be a minute amount of orange juice. You won't be able to taste it, but there technically still will be very, very small amounts of orange juice. Hopefully this refreshes your memory on exponential functions. There is a practice on exponential functions with modeling, just basic doubling, tripling, cutting things in half that we're going to try before we move on to percent changes.